Right.
Okay.
All right. Hello, everyone. We're 2 weeks late for organizational reasons, but now we're probably going to resume our standard schedule of having like roughly one talk a month. So today it's a great pleasure to introduce Marcus Sperling, who is currently at one of the house centers, the southern one in Nanjing, and he will tell us about 60 theories, Higgs branches, and magnetic quivers.
Right, then hello everyone, and thank you very much to the organizers for inviting me to the seminar. I would have preferred to, visit Australia and New Zealand in person, but this is also a great way to get to know the community. I'd like to use today's seminar to speak about the project I've been working on for roughly about the last 4 or 5 years. So it's called magnetic quivers, and before we jump into all the core details, I give you a motivation and introduction, what we are looking at and why we're looking at it. And then we're going to get a bit more technical and see what we can actually do with it in relation to 60 theories today. So first of all, the things that I'm looking at is modular spaces of supersymmetric vacua of field theories in diverse dimensions. And here we know that the modular space of these vacua, the geometry of them depends strongly on the amount of supersymmetry that we have. So in particular, if you go for 8 supersymmetries, which is quite an enhanced supersymmetry, then there's one geometry which is also fairly rigid, which is called hyperkähler. And we do have 2 prototypic examples which fit in this kind of geometry. One is what's called the Higgs branch in dimension 3 to 6. So here Higgs branch is really, we give vacuum expectation values to sort of scalar fields that transform usually in the fundamental of some gauge group. And then on the other hand, we can also have the Coulomb branch. And this one is only hyperkähler if you go in dimension 3. If you go to other dimensions, then the vector multiplet usually does not have enough scalar field to make it hyperkähler. And so you already see that there's sort of a sweet spot of 3D where both maximal branches of the modular space are hyperkähler.
Sorry, so may I ask a question? What's wrong with Coulomb branch in 4 dimensions?
Sorry?
What's wrong with Coulomb branch in 4 dimensions? Or 5?
Nothing wrong. It's a perfectly fine object. It's just not hyperkähler.
What's wrong with Kähler cone?
No.
Are you like hyperkähler cones? Okay.
I do like hyperkähler cones.
All right.
Right. So I do like hyperkähler because it's very rigid, and then we have a lot of tools to analyze these spaces. We know that 40 Coulomb branch is a perfectly well-defined object and has a beautiful geometry, but I do like it a bit more rigid. So that's why the 3D n equals 4 Coulomb branch is nice. So in order to set things off, what is a prototype example of things you will be seeing later is this 3D n equals 4 theory, which is sort of encoded in this little diagram, which is called a quiver. And it has a round node related to an SU2, meaning we have a vector multiplet with a gauge group SU2. We have a square box with SO8, meaning the global symmetry is SO8, or think about a vector, background vector field. And then we have a line in between telling you there's a matter content that transforms in the fundamental of SU2 and the fundamental of SO8. Or if you want to say, you can think about 4 fundamentals of SU2. Now this theory in 3 dimensions has the two maximal branches. Both of them are hyperkähler, and both of them are actually one of these prototypical examples of hyperkähler singularity. Higgs branch is what's known as the closure of the minimally product orbit of SO8 or D4, and the Coulomb branch is the Kleinian order Duval singularity C2 mod D4. And these are really sort of the broad and better, or the better butter and bread of the kind of geometries that we are dealing with. And I sort of have to apologize to any mathematician that is around, because for us, the modular spaces go under various names and we sort of use them interchangeably, and there has been sort of an evolution over time. We started calling them hyperkähler cones, hyperkähler singularities, and then recently we shifted more to symplectic singularities or holomorphic symplectic varieties. But sort of for physicists, it is round about the same. So why do we like these kind of geometries? It's because we have quite a lot of constructions in string theory that actually realize them in one way or another. One of the examples that I've usually been working with is what's called brane systems in type 2, which go back to the work of Fanani Whitman 96. And here for the 3D setup, it is a setup which has 3 different types of branes, which are arranged in such a way that we have 8 supercharges perturbed. So the cartoon here is we have these circles which are crossed out, which is called NS5 brane. Then we have the horizontal lines in between which connect them. Those are called D3 branes. And the D3 branes in the electric frame, they give rise to the gauge group. So this is U2 here. And then we have the vertical lines, which are D5 branes, and they are a lot heavier than the D3 branes, and therefore they give us these flavor multiplets, which is called NF equals 4, because we have here 4 of these D5 branes. Right, and now the beauty of the brane systems in 3D is that we can go from an electric frame, where we read off the fundamental degrees of freedom from the fundamental string, to the magnetic frame, where we read off the degrees of freedom from the way we suspend the D1 string. And the way we do it is we change the phase of the brane system from having the D3 brane suspended between NS5 branes to having the D3 brane suspended between D5 branes. Once we do this, we can then, in the very much same spirit as before, we can start reading off these cartoon, or what's called the quiver, in order to tell us what is the theory that is described by this phase of the brane system. And then for people that know already 3D mirror symmetry or S-duality, they would know that the quiver on the left-hand side is the mirror of the quiver on the right-hand side. Right, so that is sort of the beauty of the brane systems. We can take a whole gauge theory and we can sort of encode it in this in the way the branes intersect each other. And then we can, by moving the branes around, we can sort of have access to various phases of this theory. Of course, brane systems are not the only thing that give rise to theories with 8 supercharges in string theory. We also know there's F theory and M theory on singular spaces. And they do give us the same low energy descriptions, but the Higgs branches are still a bit more challenging than the ones we have from brane systems.
So just to clarify, so you said mirror, can that be understood in the classic mirror symmetry for branes, or is this just a different kind of duality?
Yes. So here in this setup, if you now do S-duality and just replace the D5 by NS5 and the NS5 by D5, you get the brane system, the electric brane system for this theory.
So is it S-duality or T-duality? Because I usually associate mirror symmetry with T-duality rather than S-duality.
This one is S-duality.
Okay.
Right. So it's S-duality because you exchange electric and magnetic degrees of freedom.
Right.
Yeah, by the way, any questions, please feel free to interrupt me in between, because
yeah,
I might go.
Yes. Marcus, hi. Yeah, hi. So it seems, I'm not sure I understood this correctly. It seems that there are 2 dualities that you perform from some kind of electric magnetic duality that gives you the quiver on the right-hand side, and then an extra S duality that replaces the D5 by NS5 and vice versa. Is that what you're doing?
Not really. It's quite. So without doing S duality, you can just take the electric frame and you can take the magnetic frame and perfectly well defined. And then S duality just relates them as a strong weak coupling duality.
Okay, I see now what you mean.
Right. Very good. Any other questions at this point? Okay. Right. Now we have, I've already introduced that we have a Higgs branch and a Coulomb branch, and for today's focus is going to be on Higgs branches. And you might ask, why are we still focusing on Higgs branches? Because for a long time, there has been the belief that if you have a Lagrangian theory, then you know that the Higgs branch is what's called a hyperscalar quotient. Meaning, for those who have seen supersymmetric theories, is you take the F-term modular space. So you solve the F-term equations and you quotient out the complexified gauge group. And that's what's the hyperscalar quotient. And for this, you don't need to know anything about quantum corrections, because first of all, we know that this modular space is corrected from quantum corrections. So you can just take the Lagrangian description and you get the full modular space. And we know this is classical physics. It's very, very nice. And for a long time, there was a belief that Higgs branches always kind of this phenomenon. But actually, it's not quite true. So Higgs branches are not necessarily classic exact. There are special points at which we can have extra masses degree of free entering the Higgs branch spectrum, and then we need to take them into account. And they, of course, then severely change the Higgs branch geometry. And we have plenty of examples. And these examples have not only been known since a few years, but they have been known since the 90s already. So we know, for instance, in 60, there's the physics of the tensionless strings, which can, once these strings becomes tensionless, they can enter the Higgs branch spectrum, as we're going to see in the later part of this talk. We know in 5 dimensions there's the physics of massless gauge instantons, or basically how people used to call it. They have a low energy effective description in the IR of the 5D theory, and then they want to know what is the CFT corresponding to it. And many have been trying to understand what is the symmetry enhancement of this theory. But actually, this symmetry enhancement is not only symmetry enhancement. In many cases, it's actually a Higgs branch enhancement. Right? So that's what's actually what's happening. And similar in 4D, you have the geostatus points, which are intrinsically strongly coupled, and they do have Higgs branches which are not simple hypercad quotients. So since we have this kind of challenge of the strongly coupled Higgs branches, we do need to find a way of how to describe these modular spaces. And that is precisely, yes, go ahead.
Another probably stupid question. So for me, a Higgs branch is always related to symmetry breaking. So
yes,
when you talk about enhancement, do you also see that sort of the broken symmetry is further enhanced, or how do I understand this enhancement? So is there more symmetry at this enhanced points as well?
Yes. So think about the 5D Seiberg theory. So you have SU2 with fundamental flavors, and then we know in the low energies it's some SO2N flavor symmetry,
right.
And in the conformal phase ones is E. It's an exceptional global symmetry, like ENF plus 1. So for instance, you can have E8. So what's happening is once you at the conformal phase point you have D8, but once you go away from the conformal fixed point, you do have a finite gauge coupling, and the finite gauge or the gauge coupling in 5 dimensions has the same dimension as the masses. So that is actually an explicit breaking of the symmetry.
Okay, so this process, can I understand it as some kind of an unhixing in some level, or is it different?
Yeah, you can think about that.
Okay,
that's probably a good way, because many of the things that we sort of when you go to strongly coupled points and you see enhancement of the Higgs branch or of the symmetry, you do think about as a generalized Higgs transition, because you do have some massless operators that at some point just disappear out of the spectrum. Right. So yeah, that's indeed a good way of thinking about it. Right. So the point of now this the slide was to point you to this question that we do need to find a technique to address these questions, and that the solution that we found, or the solution that we proposed, is precisely the magnetic quibble. And the way it works is that actually now we turn around the sort of the thinking. Previously, for a long time, what people have been doing is saying the 3D N-equals Coulomb branch is sort of hard because it has quantum corrections, and we sort of want to understand it, but we can't use the Lagrangian data solely to describe the quantum corrected space completely. So what people have been doing is they use the Higgs branch of the mirror dual theory and then study the Higgs branch and then say, okay, since by mirror symmetry we know what's the Coulomb branch. But actually, we can now turn this logic around. We say we have gained enough understanding of 3D Coulomb branches because we now know that a quantum corrected description of the Coulomb branch is possible by using what's called monopole operators or dressed monopole operators. So these operators are in contrast to the things that you usually would do in the Higgs branch. So it's not simply a gauge-invariant polynomial of the microscopic field, but actually it's sort of defined as an insertion in the path in the code. And these operators turn out to be a very nice basis to describe the quantum corrected Coulomb branch. And once we appreciate this kind of approach, we can actually compute various quantities for this Coulomb branch. And they range from very simple things like dimension, which is just a simple number, to global symmetry, which is still sort of just a group. But then you can go ahead and you can start computing a generating function for the chiral ring, which is called Hilbert series. You can even attempt to compute the chiral ring itself, so all the generators and relations. This is usually the hardest part, or something which we call the phase diagram or the Hasse diagram, which is sort of in between. And most of the techniques that we now use are basically relying on this 3D N-equals-4 Coulomb branch Hilbert series, which has been introduced in 2013. And this has then also led to quite significant developments in the math literature. Now, how do we proceed? The proposal is the following, that we have a theory in dimension 3 to 6 with 8 supercharges at a given phase. And this phase can be either the weakly coupled phase for which we already know what's happening, or it can be any of these strongly coupled phases or anything in between. And we proposed as for this phase, in order to describe the Higgs branch, we can derive an auxiliary theory, which we call the magnetic quiver, and we use the 3D n equals 4 Coulomb branch of this magnetic quiver to provide an equality in terms of modular spaces to describe these Higgs bunches under question. Right? So we use the improved understanding of the 3D n equals 4 Coulomb bunch to describe these sort of complicated and strongly coupled Higgs bunches in high dimensions. We're not aiming for any duality on the level of field theory. It's solely a proposal for the space of vacuum. Right? And then you might say, okay, sounds very nice, but how do you actually do this? And the starting point is again, we use brane systems in type 2 because here we already know from the intuition at 3D n equals 4 that we do have an electric phase and we do have a magnetic phase, and this generalizes to high dimensions as well. Right, now is either the time for questions or just to show you that this has been going on recently for quite a bit. So there are various groups that have been working on various aspects. So there's the 6D story that I'm going to be telling you today. There's something in 5D, which we have been working on brain webs, but also people have been working on M3 and on toric Kabeljau. Or we can even go to 4 dimensions and address some of the proposed classifications of the rank 1 and rank 2 SCFTs or the S4 theories. But this is sort of advertisement to show you it has been going on for quite a bit now. Right, if there are no questions at this point, I'll go now to sort of the more detailed part. So it's going to be a two-part presentation. The first one is we're going to talk about M5 branes on an A-type singularity within a 9-ball sometimes. And after we gain some familiarity with the way it works and what we can do with it, we can go to a more complicated setting, which is M5 branes on a D-type singularity. And then we're going to see that we can actually find still very surprising and exciting modular spaces, although many people would believe that 6D theories have been partially classified for quite a bit now. Right? Okay. Now let's start with the first one. So the setup that we're looking at is we have a...
Sorry,
yes.
Can I ask you a question?
Of course.
Can you show models?
I was about to do that, but yes.
Not the brain picture, just field theoretic models.
Yes. So like this one. This right. So this I would call
this is not the model. This is just again some picture. Can you show me just field theories?
This is a field theory. I can use this graph
to
write it down the Lagrangian.
For God's sake.
I can show you. I haven't written it on the graph, but the point is not to write down the Lagrangian all the time. But the point is to put all the data of the Lagrangian into this graph. So if you want, we can take this graph and we can dissect it a little bit more further, right? So the round node, what is the round node? The round node is a 3D n equals 4 vector multiplet, right? So you have a gauge field, you have 3 scalar fields in the adjoint, and you have the corresponding superpartners.
Okay.
Right. Then this line here, what is this? These are hypermultiplets. Right?
Hypermultiplet. So, what's realization of hypermultiplet? R-symmetry group SU2 cross SU2. Hypermultiplet transforms in which one?
Yes. So the hypermultiplet transforms as fundamental in one of the R-symmetry groups and transforms in the trivial of the other R-symmetry group. The vector multiplet transforms.
There is some message, but what if I just take hypermultiplets in bifundament?
Without a gauge group.
No, my question is about R-symmetry group.
Yes, you take a hypermultiplet in the bifundamental. It is still transforming as a fundamental of one of the R-symmetry group factors. It is trivial in the other one. Because the 3D n equals 4 has 2 factors of R-symmetry. One is acting on the hypermultiplets, the other one is acting on the vector multiplets. And the whole point of having these 2 maximum branches with hyperkähler geometry.
Hypermultiplets can transform in can be checked with respect to both R-symmetry groups. This is the point.
You're perfectly correct. You're perfectly correct. We have a hypermultiplet and we have a twisted hypermultiplet, right? The twisted hypermultiplet is the hypermultiplet, and I just reverse what I mean by the R-symmetries. The same I can do with a vector multiplet. I can have a vector multiplet which transforms in the vector representation of one of the SE2Rs. I have the twisted vector which transforms as the vector in the other one. You're perfectly correct. So if you, for instance, look at the left-hand side and you allow me to use a fundamental string, then you get the hypermultiplet and the vector multiplet. If we use the setup on the right-hand side and reduce the D1 string, then you would get twisted hypermultiplets and twisted vector multiplets. Then what S-duality does, it exchanges Higgs bunch Coulomb bunch and it reverses the order of the asymptotic groups.
You see, twisted hypermultiplet is terminology that is not used in three-dimensional supersymmetry. I'm sorry to say that. So you can use that terminology in Euclidean supersymmetry, but not in space-time supersymmetry.
I see. Okay. Okay. Does it answer your question about the quantum field theory content, or?
No.
I see. Okay.
But, okay, that's fine.
Okay, sure.
We have fire alarm here, so I have to go.
I see. My apologies for that. I hope you'll be safe. Right. Let's proceed. Any further questions before I show you more cartoons? Okay. Right. So the 60 setup that I would like to speak about for a bit now is realizing M theory as follows. We have M5 branes and we have an M9 brane, or M9. Right. So the M9 brane is extended in all but one of the 11 space-time dimensions, and the one that is not extended in is the X6 directions. So I'm just going to draw it as a line in the other 4 that I've chosen to draw. The A-type singularity is occupying a real 4-dimensional space, right? And that is chosen to be the 7, 8, 9, 10 direction. And then the singularity is then basically this line, because the singularity is then extending in all of the other directions. And then I have M5 branes, multiple of them. And these M5 branes, they fill basically all the remaining spacetime, and I just draw them here as points. Now, as you can see from these M5 branes, I can put the M5 branes in various places, right? So I can put them on the singularity, I can put them away from the singularity, I can put it on the M9, away from the M9, I can put them coincident, I can put them separate. And all of these different choices of where to put the M5 define different phases of the 60s theory. And we want to study the corresponding Higgs bunches. Now, what we're going to use is the dual type J picture, meaning that we dualize the M9 into the 08 minus and 8 D8 branes. The A-type singularity dualizes into a stack of K D6 branes, which I just denote by these horizontal lines, and the M5 branes become NS5 branes. And it's sort of the same cartoon holds. I can have the NS5 branes away, separated on top of each other. So that's sort of the phase structure. Now, in order to proceed, I need to tell you a little bit about the low energy description of these theories. And that is where the 61,0 theory is coming to game. Contrary to the 2 supermultiplets that we have just talked about a second ago, now we have 3 types of multiplets that we need to take into account. We have the vector multiplet in 6 dimensions, which does not have a scalar component. That means there's no Coulomb bunch in 6 dimensions. We have the hypermultiplets, which do have 2 complex scalar fields. So we have the usual quaternionic Higgs bunch, and we have a tensor multiplet. So the tensor multiplet is rather new in compared to the other dimensions. It contains a 2 form, which then has a 3 form gauge field, and it has 1 real scalar field. And this one scalar field is very important because the vacuum explanation value of this scalar field actually sets the inverse gauge coupling squared. So that means the gauge coupling is really not a parameter, but it's actually a vacuum expectation value in 6 dimensions. And in terms of the brane system that you've seen before, it's actually that the separation between NS5 branes or M5 branes, so the relative distance in X6 direction, sets you the scale of this vacuum expectation value, or this 1 over gauge coupling squared. Right? So then, when you recall what I told you before, that this various arrangement of M5 brane or NS5 branes, whether they are on top of each other or away from each other, this defines the different phases. Then we also know that putting NS5 branes sufficiently close or even on top of each other is actually a strongly coupled phase. So, and then we want to know what is precisely the Higgs bunch of these infinite coupling transitions. And we have 2 prototypical examples that we can talk about. One is the M5 brane moving into the M9, setting 1 gauge coupling to infinity, which is called the small E8 instanton. Or we have 2 M5 branes becoming coincident, which we call the discrete gauging transition. And for these, it's now basically the question, how do we address these corresponding Higgs bunches at these strongly coupled points? So,
Marcus?
yes.
Sorry.
Yes.
Could you remind me? So if you have a single NS5, the theory is a 6D n equal 1,0 with a tensor. That's on a single NS5.
Yes, on the single NS5, you do have a tensor, but an overall tensor decouples, right? So an overall tensor multiplet decouples. So if you have n NS5, only n-1 of them contribute dynamically to the and the overall decouples. It's just a position.
I see. Okay, thank you.
Right. Right. Also, just to remind everyone, so there's some anomaly cancellation conditions in 6 dimensions. You can have a tensor multiplet without having a gauge multiplet. That's perfectly fine. But you cannot have a vector multiplet without a tensor multiplet. So as soon as you have a vector multiplet, you also have to have a tensor multiplet, but not the other way around. Now, this is just some notation. Sort of we combine various types of information in sort of a quiver, which I would like to say it encodes all the information that we need to know about the field content. Basically, just for the expert maybe, you can realize the same thing in F theory, on which you have an elliptic calabi-Yau with a base, which is composed of a linear chain of -2 curves and at most -1 curve. So the -1 curve is there if you have the M9 wall present, and if you consider the setup without the M9 wall, you just have a chain of -2 curves. And then the -2 curves basically are, you can think about it as in between these NS5 intervals. And what we do is we have this quiver that gives us the field content. And for each of the gauge nodes, we now denote what is the corresponding curve, because depending on the type of curve, there's different anomaly cancellation conditions which are important. So if we have a standard SUN on this simple looking -2, we have the standard anomaly constraint telling us that the number of fundamentals has to be 2n. And we see, yes?
Sorry, another stupid question. I say elliptic calabi-Yau threefold. So these are non-compact calabi-Yaus, right?
Right.
So when you say, so the elliptic fiber must be compact because it's F theory. So where is the non-compact direction?
Well, you already resolved that thing, no? And then you have you take the non-compact direction. Fair question.
Or are these calabi-Yaus compact? But I thought these ALE type brane constructions, they're like non-compact.
It should be non-compact.
Yeah. So that's why when you have an elliptic calabi-Yau, that means elliptically fibered usually. So the fiber direction.
That's right. That's right.
Should be compact, then, I suppose, but I'm not sure. That's why I'm asking.
Right. So here, what you have, so you have the base curve is what these curves of self-intersection -2, and then of each of them you have different fiber types. Right. So here you have a fiber type which is called I think IN, which gives rise to this SUN type gauge algebras. And then the way it looks is basically you have the affine Dinkin A-type diagram for the P1s in the fiber. Right. So that's sort of how it works. But really here it's more like a bookkeeping thing, because so the different anomaly. So the gauge theories or the low energy effective description in 6 dimensions are fairly constrained by anomalies, and keeping track of this type of curve they come from is very nice, because then we can know we immediately can read off what is the anomaly constraint, even if you go to models which are not obvious from brake constructions. Right. Okay. Let me show you an example, and then we're all going to be very happy, I hope. So the first example we're going to do is the simplest, or one of the simplest one you can look at. We have 2 and 5 branes which become coincident. And we take a very simple A1 singularity, and we have no funny business. We have just 2 NS5 branes. We have 2 D6 branes, and I have chosen to terminate the semi-infinite D6 brane just on D8 branes, and we have just 1 D6 ending on 1 D8 brane, so everything is very, very pleasant. We know that the corresponding 6D theory is precisely what I've already shown you before. It's an SU2 with 4 fundamental flavors. And now we know there's one additional tensor multiplet, which is the 6D part to the story. Now, if you want to understand the Higgs bunch, we first of all need to understand there's not just 1 Higgs bunch, there's 2 at least. And we talk about the finite coupling Higgs bunch for the beginning. And here what we do is the very same logic as before. Here we said this is the way we usually read of a quiver theory for brane construction, saying we use the fundamental string, and we have the d6 brane suspended between the NS5 branes. Now we go to the magnetic frame, or we go to the Higgs bunch phase of the brane system. And as in 3D, the Higgs bunch phase of the brane system is realized by suspending the d6 branes between the d8 branes. And then the NS5 branes need to be lifted up. This is now the Higgs bunch phase of the brane system. So we haven't done anything. We just went to a different phase. And now we just start reading off the description for the magnetic quiver by identifying the degrees of freedom. And we know that the d6 brane between the 8 branes can move, and it precisely gives us 1 quaternonic dimension for the model, or 1 quaternonic degree of freedom for the Higgs bunch. So we associate to this single d6, we associate a u1 here. For this d6 branes, 2 d6 branes which are here, we can move them both together. And if we put them on top of each other, as before, we would expect an enhancement to u2. And the same with the u1 on this side. Now, the new part compared to the standard brane systems in 3D is that we say now in 6 dimensions, as a rule of thumb naive argument, you would say the NS5 brane and a d6 brane suspended between 2 d8 branes sort of have the same dimension of the world volume. So we should consider them on equal footing. Meaning on equal footing, we say both of them contribute a U1 magnetic gauge field. And now, so this will be the proposal for the magnetic quiver, just read up from a brane system. Now, what do you do with this besides looking at the graph and saying, okay, this doesn't tell me much? Now you can use a whole lot of exact machinery. You can use this to input into an object which compute you the Coulomb bunch Hilbert series of this object. Once you start computing this Coulomb bunch Hilbert series of the subject, you're going to realize that the Coulomb bunch we described with this magnetic quiver is nothing else than the minimum near-pattern orbit of S weight. Or for those of you who already have seen a bunch of quivers before, you realize this is a defined default Dinkin diagram, and the ranks of the gauge are nothing else than the Dinkin labels of the diagram. Right? So this is sort of the zero-order trivial check that the magnetic quiver is not completely outrageous, and it gives you the consistent answer at finite coupling. But of course, this already we have known before. Now, what we really want to know is what happens if we go to strong coupling. Right? Strong coupling is now realized by putting these NS5 branes closer and closer and closer together. So at the end of the day, we put them on top of each other, and we would basically be saying that we're now looking at the conformal field theory associated to this tensor bunch description. So for this, we can use the same brane system as before. Now, the only thing that we need to do is, as soon as the NS5 branes are separated, there's sort of a permutation symmetry between them because we can't distinguish them anyhow. But now we put them on top of each other, meaning that we actually gauge this as 2. And the brane system now is that the NS5 branes are on top of each other. So the only thing that becomes modified in the magnetic quiver is this top part, because we know that the d6 branes, they haven't changed. Their degrees of freedom are not hindered or anything. It's just the same as before. Now the only thing is that these NS5 branes are on top of each other. But also note that the NS5 branes are away from sort of the rest of the brane system. So locally, you can think about them as not having 8 supercharges, but 16 supercharges. Right? And if you have 16 supercharges, you would say it's not just a U2 gauge node, but it's actually in a joint as well. Once you may accept this proposal for the magnetic quiver, you can again sit down and compute your Hilbert series. Once you compute your Hilbert series, you're going to see that so the Higgs bunch of the infinite coupling, the only way we know how to compute is by the Coulomb bunch of this object. Now, if I compute you the Coulomb bunch of this quiver here, you're going to find that it's the next to minimum near-pattern orbit of SO7. So it's one of these mathematically very well understood spaces. Now, in terms of what we have done, we have said we gauged an S2 permutation symmetry, meaning we actually have taken an S2 hyperkähler quotient for the finite coupling Higgs bunch, which would mean that we actually take an S2 hyperkähler quotient of the minimum near-pattern orbit of S8, which is a fair statement if you compute a Hilbert series. And this statement not only holds for this example, this statement of having this discrete quotient here holds for any of these examples where you do precisely this manipulation. But here in this example, we have further confirmation that this is actually a correct way of thinking, because the discrete hyperkähler quotients of near-potent orbit closures have been mathematically already worked out in '97 by Berlinski and Coincide. Right. So the moral of the story is looking at Higgs bunches which realize mathematically well understood objects is very, very helpful for us in order to refine how we think about the Higgs bunches of more complicated setups. Right. Okay. Now, if there's no question about this, let me go to another example which emphasizes another point. So now we're going to go to 3 and 5 branes, and we're going to see that we can realize the theory which has the same classical Higgs bunch, but actually the phase structure of the infinite couplings is completely different. And the reason is that we have now this tensor multiplets that contribute to the game. So the starting point is we have 3 and 5 branes, again, the A1 singularity, but now we slightly modify the boundary conditions a little bit, meaning on the right-hand side, we still have 1d6 ending on 1d8 as before. So this is a very vanilla brane system. On the left-hand side, we do have 2d6 ending on the same d8. This boundary condition now is different to before because there is, in brane systems, there's a rule which is called S rule. It's a rule about what is a way that preserves supersymmetry of dp branes ending on dp plus 2 branes. Here, the statement is we cannot have more than one d6 brane suspended between a d8 and the same ns5 brane. So meaning here that one of the d6 branes can end on this ns5 brane, but this d6 brane cannot end on the same one. It actually has to go to all the way to this one here. And this is then important to remember once you're going to go to the phase of the brane system where you read of the quiver description. So once you do this, you get a quiver that sort of looks like this. You have an SU1, you have an SU2, and you have 3 flavors, and you have 2 tensor multiplets because you have 2 differences between ns5 branes. And now if you're inclined to deep theory, you say, okay, SU1 is not really dynamical. I think about this as SU2 with pro-fundamental flavors. And at finite coupling, you're perfectly correct. At finite coupling, you do the same logic as before. You take the brane system to the Higgs bunch phase, meaning you suspend the d6 between your d8 branes. You start reading off your magnetic quiver, but the same logic as before. So you get a U1 for this d6. These 2 d6 gives you a U2. And now you have 3 ns5 branes which are separated. So you have 3 of them here. But now, remember, this is just a weirdly drawn affine defaulting diagram. Right? So we already know what is the associated model space is, again, the minimum independent orbit of SO8. So we know they do have the same finite coupling Higgs bunch. But now if you want to go to infinite coupling, you already see there's various ways of doing that because you have 3 ns5 branes, so you can choose. Do you collide 2 of them on the left, 2 of them on the right, or how do you do it? And then there's another phase where all of them are coincident. So we already see that having these different possibilities gives you a different infinite coupling phase structure. So what we see here is that the first sort of semi-infinite, let's say semi-infinite structure, I take 1 gauge coupling to infinity, is I have 2 ns5 branes together, I read a magnetic quiver, and that is, again, the one we have seen before, just drawn in a weird way. So it gives you the minimum independent orbit of SO7. But now going to infinite coupling to the conformal fixed point is I put all of them together, and I read the magnetic quiver, which is now 1, 2, 3 with an adjoint. Again, you can take this object and you can start computing your exact Hilbert series. Once you start computing your exact Hilbert series, you see that the outcome is that this Coulomb branch is nothing else than a subregular near-potent orbit of G2. Again, first of all, we do see that the finite coupling Higgs bunch is very, very different from the infinite coupling Higgs bunches. We also see that physically what we have done, we have put all of the branes on top of each other, so we have gauged an S3 permutation symmetry, which tells us that the infinite coupling one physically is realized by an S3 hyperkähler quotient, which should be the S3 hyperkähler quotient of SO8 in the near-potent orbit. Again, you can verify this by Hilbert series, and you can get further confirmation for this case from the known result of mathematics that the G2 subregular is really just the S3 hyperkähler quotient. Right?
Sorry, again,
yes.
A terribly naive question. So
yes,
you said the Hilbert series essentially count the Carroll
yes.
state. Right. So by computing the Hilbert series for different theories, so your conclusion is that if they are the same, the theories are related. Is that kind of an invariant, or what information do you extract from the Hilbert series?
So the Hilbert series is the but it counts you the Gaussian band Kepler operators if you think about the Higgs bunch. Right. So in terms of if you think about in terms of Higgs bunch, what you do is you build Gaussian band combinations out of the fundamental fields. Fundamental fields have a definite R charge, and what you do is you take the U1 carton of the R charge as a grading dimension for these vector spaces, which have then a given dimension, and you just sum them up. And we do the same thing for the Coulomb bunch. So we compute the C star character of the Coulomb bunch or of the Higgs bunch if you want. And this one can be refined with respect to global symmetry. So here, right? So here I have everything is U, so I can turn on 3 additional U1 fugacities, such that all of these statements are not just in terms of like one variable and a bunch of dimensions, but actually you can make this a match between one grading variable and characters of the global symmetry.
Thank you.
Right, and the point is really that so if you take one of these theories and you compute the like a standard partition function, then that one is argued to be invariant under RG flow. Right, but here, I mean, the point we're making is that the Higgs bunch is not invariant under RG flow. Right, so then that's why for each of these phases we propose a different magnetic quiver, and then we compute the Higgs bunch generating function, because we do know from known examples that our additional operators do enter the Higgs bunch spectrum, so it cannot be an invariant. And so that's why we can't use partition function in this sense. Right. Any other questions?
Actually, yes.
Yes, sure, please.
Naive question. Is there any results for partition functions using localization for this kind of theories?
What do you want to compute? Do you want to compute a 60 partition function or 3D partition function?
Yeah. 60.
Yes, for 60 partition function, there are plenty of results.
Yeah.
So if you, for instance, go to this one, so this one is quite a famous thing, because so what is famous about it is that on the tensor bunch you would see an SO8, but then on the fixed point you see an SO7 global symmetry. And this has first been confirmed by computing the partition function. So there's a paper by Michele Del Sotto and Guglielmo Lockhart. They showed that the elliptic genera actually then, although you start writing them as SO7 variables, you can rearrange them in terms of you start with SO8 and you realize later it's SO7.
Can you derive like the Hilbert series from this partition functions, or get some information on the Higgs branch from that? What can you get?
I wouldn't know how to get the Higgs bunch from this partition function.
No.
So there's some like 1 or 2 years ago there was some confusing observations. So people started computing elliptic genera for like non-Higgsable 60 theories. Like for instance, the SU3 on a -3 curve has just an SU3 gauge group, has no matter. And then you start computing the elliptic genus, and you find it's going to be the one string elliptic genus is going to be something like the SU3 one instanton Hilbert series. Right. So, but that basically just means you describe the elliptic genera, and it's basically just a one instanton effect. So there you do see a relation of the elliptic genus to the Hilbert series in a certain limit, but that only comes because you're looking at the thing which is already describing an instanton, and you take a certain limit where you agree with another description of the instanton moduli space. For generic 60 SFT, I don't know how to see a relation between the partition function and the Hilbert series of the Higgs bunch.
Okay.
Right.
All right, thank you.
No worries. I mean, the more questions you have, the better it is. I mean, I'm certainly not going to finish anymore, but I mean, I have about 5 minutes left.
Oh, is
Right. Right. Maybe I show you. Yeah, maybe I use the 5 minutes to show you one other cool thing, and then we can go into discussions or whatever. Right. So the second thing I wanted to show is the second type of infinite coupling transition that we have in this example, which is called the small E instanton transition. And that is precisely what happens if you take the M5 brane into the M9. So you start with this cartoon, NS5 brane, the 08 minus, and they're far away from each other. In terms of reading the 60 tensor bunch or the 60 low energy quiver description, you would get an SP, what's called an SP0. Simply because if you would start having these 6 branes in between here, then the orientable projection would tell you that the gauge theory living on the D6 brane is a symplectic gauge group. So now this is sort of the 0 rank limit of this kind of story. And then you have SO16 flavor symmetry just because you have 8 D8 branes in total and plus 1 tensor bunch, plus 1 tensor multiplet. And we immediately see that this theory has no Higgs bunch. It's just trivial. Either because you see there's no D6 branes, or you see the gauge theory just trivial. But now, the important point is now we can start from something that's trivial and go to something that is wildly non-trivial. And the way we do is we shrink the -1 curve, or we take the gauge coupling to infinity. What that means in terms of branes is we take the NS5 branes, we move it through the D8 branes. So every time we do that, we have brane creation. But this phase is nothing else than this one, because the distance here is still finite. So that means that all of these 6 branes are suspended between a D8 and an NS5. So they're completely frozen, they're non-dynamical yet. The magic happens once I take the NS5 really onto the locus of the orientifold. If I do that, I need to remember it's an orientifold, right? So an orientifold is roughly like a mirror. So I have the NS5 and I have the mirror image. And once I put them on the orientifolds, I see both of them at the same time. So that's why I have 2 of them. And once they match, the connected D6 branes, now they can start reconnecting among each other in a way that preserves supersymmetry. That is why you have this sort of funny cartoon that the D6 go from one and then through the orientifold to the other. And this is now the description of the Higgs bunch phase in terms of the brane system. And now we do the same thing as before. We start reading of the magnetic quiver. And the left-hand side or far away from the orientifold is the same logic as before. It's just a linear chain of gauge groups that start increasing. And then at some point, you're going to come close to the orientifold. And then we know how to read this kind of thing because we know how D-type Dinkin quivers are realized in string theory or brane construction, because we know there's a bifurcation. There's this 4 here, which is the 4 here, and there's some 3 here, which is this 3. So this is the D-type bifurcation we already know from string theory. Now, the only new thing that we have to remember is that the NS5s are now sort of taken into account as dynamical magnetic degrees of freedom because we can move them along the orientifold, and we say they do contribute Higgs bunch degrees of freedom. So I attach a 2 here. And now you should be very, 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 very happy because this is nothing else than the affine E8 Dinkin diagram. If I start now computing the Coulomb bunch of this object, which is supposed to be the Higgs bunch of infinite coupling, you want to find this is the minimum Newton over the field. Now you might ask, so why the heck is this happening? Well, there are 2 things to remember. First of all, the M9 does carry an E8 global symmetry, right? Second of all, we started from an M5 brane being away from the M9 brane. Then the relative distance between them is parameterizing the tensor bunch, or the tensor bunch modulus. But now if I put them together, I basically have a vanishing tensor multiplet. But there's a gravitational anomaly cancellation in 6 dimensions, which tells you that the number of hypermultiplets plus 29 times the number of tensors minus the number of vector multiplets has to be constant under any circumstances. But we have seen there's no vector multiplet to begin with. So the only thing that really can happen is that we get 29 new quaternionic degrees of freedom. And then there are not that many spaces that are of 29 dimensions and have E8 global symmetry. So having this minimal Newton of E8 appearing here is a very natural and very important confirmation that the magnetic quiver proposal works very, very nicely. Right, and then sort of short, let me maybe jump just to the summary and the outlook, and then I can talk about this later if somebody has any questions about this. And indeed, it works. I'm surprised. Very good. So what I wanted to sort of convey today is that the magnetic quiver is sort of a tool that we use in order to understand Higgs branches of higher dimensional theories with 8 supercharges. And it is very computable because on the one hand side, you can do many operations on branes, you can do many operations on graphs themselves. And you sort of have two types of information that you have. On the one hand side, you have an exact computation of an operator spectrum generating function, which is the Hilbert space. And you can refine this with respect to global symmetries, you can do partial symmetry breaking. It's a very nice and computable tool, and you can compute this exactly in contrast to like a supercompound index. On the other side, something which I haven't talked about today is called a phase diagram for the sort of Higgs mechanism and generalizations. And that one is very, very nice if you really want to nail down the geometry of the modular space in more detail. And everything what I've told you today was in principle for 6 dimensions, but you can also apply it to 5 dimensions, 4 dimensions, and for 3 dimensions, of course, we already know. And in principle, I wanted to show you a search for interesting Higgs branches, meaning near-planet orbits, for instance. They're very nice because on the one hand side, they are mathematically well understood, meaning that we do have a lot of information about them. And it's also very interesting to see what kind of 6-dimensional theories do realize these known spaces. But this doesn't mean that we can't do the others as well. The other more complicated theories, which I haven't talked about it today, we do have an algorithm which allows us to study the modular spaces. It just their modular spaces are just very complicated and very messy. So if you want to study them in the same amount of detail as we study the near-planet orbits, then you better have a good motivation for them. And things I haven't shown you today is that there's this whole machinery which is behind it. So I just leave this as a cartoon, and if you have further questions, then please feel free to ask.
Thanks, Marcus, for this very interesting introduction to modular spaces of 6D theories and their geometric realization. Yeah, are there any questions?
These people are still around. Yes.
Well, I have a lot of questions, of course, but
Sure.
I do ask people. On your previous slide, you said you're looking for interesting Higgs branches. So I only follow this, geometric engineering business from a distance. And it seems to be very powerful in understanding, how the parameter space of these theories. But what always strikes me is, how do you come up with your interesting models? I mean, what's your sort of guiding principle to find interesting phenomena in gauge theories in this context?
That's a good question because so there's one example that I haven't shown. So did this kind of example here, just to tell a little bit. So this is an SU3 without any matter content. It's on a -3 curve. So there's sort of the fundamental gauge theory you can have on a -3 curve. And this is an empty -1 curve. So there's an E8 in here. There's an E8 global symmetry in here, and the SU3 has to be gauged inside the E8. So that the global symmetry remaining is an E6 because it's the commutant of the E8, the commutant of SU3 inside the E8. And this then gives you a good chance of being something interesting, because this one doesn't have any matter, so it's really just a gauge theory which is now gauging the minimum idiopatent orbit of E8. And then, as it turns out, the modular space is really just an E6 idiopatent orbit closure. And the way to see it is that you have this empty -1 curve. And this one has this exceptional symmetry. And now we just put it together with something that is small enough that makes it non-trivial. Because if you go to the next one, it would be like an SO7 gauge or something. Then first of all, the commutant is just an SO9. It's not exceptional anymore. It's not that interesting, maybe. But also it has a matter content, which just makes it more complicated to understand. So really, you look for something that is simple enough, but also has some unusual features. And in this case, it's usually better to go to like smaller examples than to very, very big ones. Right, so minimal cases is always a very nice way of looking for them.
So of course, the complete sort of program would be to have like a full classification of these 60 theories and to understand every type of transition and phenomenon. So can you get an estimate on how far along you are with this program? Is this feasible?
Right. I mean, so if you think about the F theory or the F theory sort of construction works by having these curves of like -n, and then you have like 1, 2, 3 up to 8 and then 12. So what we do understand is the -1, the -2, the -4, and a little bit the -3. Because those we can still sort of engineer in with branes.
Things to sort of study.
Sorry?
But there is a finite set of things to study.
Yes, in principle, there's a finite set of things to study. And sort of now we're sort of reaching the limit what we can do with brain systems. So now we then really need to go and work out the more complicated things. Right? Because even this one, I mean, I haven't talked about it today, but you see there's something in red here. In principle, that means -2 D6 branes.
Okay.
Right. So this would already be like a negative number of branes. And this is already something very non-trivial because it's a non-standard brain configuration, but it's still sort of useful to study these Higgs branches.
Okay, so is there a duality frame where you don't have -2 branes? Does this translate into something comprehensible or sensible in a brain language?
Right. So the point to appreciate is that this pops out if you do like the standard machinery for boundary conditions of D6 ending on D8. And then there has been work by Norbert Macarea, Tom Budelius, maybe Alessandro Tomasello. They've shown even if you have these negative numbers and you still just sort of use this input data to compute the anomaly polynomial in 60, you get something well defined. Right, so they showed it's not completely nonsense. So then we just follow the same. We got inspired not to give up immediately. So we used that, and we used standard brain arguments then to study the Higgs branch. And of course, this kind of thing we don't get from the branes. We sort of get it from the F theory people. So that's why we have this combination of the diagram and the curves, just to keep track of what we are looking at. But still, in this sort of negative thing, you can go to the Higgs branch phase, and in the Higgs branch phase, there's no negative branes, just a standard brain system. But you can't just go to a weakly coupled low energy description. And so that's sort of the funny part.
Okay. Okay, I think. Are there any further questions? I shouldn't ask all the questions. Check the chat. All right. If not, then I would say we thank Marcus again for this very interesting talk into a very complex subject, and see you all for the next talks. And I think we can stop the recording now.
Yeah, thanks, Marcus. Sorry, I had to go. I had an important phone call.